So in this lesson, we're going to talk about two things. One, we're going to talk about hybridization of atomic orbitals. And secondly, we're going to talk about sigma and pi bonding. And so in your notes, this is going to be a little bit back and forth. I'm going to go a little off-road, so to speak, with the notes. So, in putting these videos together, a good adage sometimes is, do you want it totally perfect or do you want it today? So this is one of those instances where I think it's important to get it out to you today. So it might be a little disjointed and jumping back and forth, so it's not totally ideal, but still will get you the bulk of the main information that you need. So when we think about carbon and we write its configuration 1s2, 2s2, 2p2 for the 6 electrons that it has total, if we were to draw that out as an energy orbital level diagram, we would see what you see here, in that the carbon would only have 2 half-filled orbitals, which would mean that it could only form 2 bonds. Yet we know that carbon preferentially forms 4 bonds. It's tetravalent. And so this typical way of distributing electrons according to the Aufbau principle doesn't jive with what experimentally we know to be true, the fact that carbon can form 4 bonds. And so if we consider taking an electron that is in the valence shell, the 2s sublevel, and promoting it or exciting it, providing it with additional energy to get up to the 2p orbital that's empty, now what we have are 4 half-filled orbitals, so half-filled orbitals capable of forming a bond. So that gets us at least in the realm of being able to explain how carbon can form 4 bonds. And you might say, well, I thought Aufbau said we couldn't fill electrons in until previous energy level was completely filled up, and that's true. However, there are some exceptions, and one exception would be when you think about, in order to get the electron up there, that's going to require an energy input. But the kickback that we get from that, from having that extra electron in the 2p level, is now the 2p level is half filled. And so you have a symmetric arrangement of electrons within that sublevel. And as we've seen, time and again in chemistry, symmetrical arrangements tend to lead to stability. And so yes, there's an investment of energy, but the return on investment in the stability that is obtained helps to offset that cost. So we still have a problem though, because in looking at this, if this were the way that carbon had its electrons, then 3 out of those 4 bonds in methane would have a higher energy than the 4th one, and 1 out of the 4 would be lower in energy. But the evidence, the laboratory data, doesn't support that. All 4 of those bonds have the same bond energy, they have the same bond length, they are in fact equivalent to one another. So to explain how we can have 4 equivalent bonds around carbon, this is why we need to introduce the concept of hybridization. Now, before we can talk about hybridizing atomic orbitals, we need to remember a couple things about atomic orbitals themselves. Remember that s orbitals typically have a spherical shape to them. Whether it's 1s or 2s or 3s, doesn't matter. All that would change would be the size of the sphere. As the coefficient gets bigger, the size of the spherical orbital gets bigger. P orbitals have a characteristic dumbbell shape to them. They have 2 lobes, and there are a total of 3 orbitals for every p sublevel. And so you would have one along each of the axes. Okay, so that one would be 90 degrees to the first, and then you would have this one 90 degrees. So putting them all together would look something like this. Okay, so that's your 2s and your 2p sublevels. Then we're going to take all 3 of those orbitals and we're going to put them together and create a hybrid orbitals. Okay, and we're taking a total of 4 orbitals and putting them together. So we put 4 in, we get 4 out. And the 4 that we get are going to be symmetrically arranged, right? So when we have 4 domains, we're going to take on a tetrahedral type arrangement. And the energy of each of those is also going to be equivalent. So you can see here that rather than having 3 out of the 4 at a higher energy, 1 out of the 4 at a lower energy, when we hybridize, we get 4 equivalent degenerate, and again the word degenerate means equal in energy, orbitals. Okay, now a couple things to note here. Note energy-wise where these 4 hybrid orbitals are. They are in between the energy of the lower 2s orbital and the higher 2p orbitals. Not just that, they are closer to the energy of the 2p level, and if you think about why, 3 out of the 4 orbitals are that higher energy, so that's naturally going to skew the energy of the hybrids so that it's closer to that of the 2p level. Another thing to notice, we would call these sp3 hybrid orbitals. And we'll see there are other types of hybrid orbitals, sp2s and sp. And there's some others as well, but we don't typically get into them too much in organic chemistry. But you might say, well, how do I know what the difference is? How do I know how to name it? Here's an easy way. However many hybrid orbitals you have, the sum total of your exponents of the s and the p should add up to the total number of orbitals you have. So you've got 1s, 3p. So that's a total of 4 orbitals. We've got 4 sp3 hybrids. You might say, well, okay, but how do I know that it's sp3? Well, ask yourself, what did I hybridize to make these hybrids? I used 1s and I used 3p orbitals. Hence, I got 4 in, 4 out, sp3 hybrid orbitals. Now, to try and understand what these hybrid orbitals are like, we can get the whole concept of putting orbitals in and getting orbitals out. But what is their true nature like? Well, just the same as if you had 4 cups of Kool-Aid, 3 blue and 1 yellow, and you poured them all into the same pitcher, and then from that pitcher you've poured 4 glasses of Kool-Aid out, you would get all 4 with the same color of Kool-Aid, probably a bluish green because more of it was blue. And the taste of it would be somewhat in between. You'd have probably a hint of the lemon lime and quite a bit of the blue raspberry or whatever the flavor happens to be. Well, the same is true of the hybrid orbitals. The characteristic or the nature of them, from their shape to their size to their arrangement, is going to be sort of a hybridization or a mishmash of them. So take, for instance, these sp3 hybrid orbitals that we were just talking about. We know that s orbitals are spherical in shape, p orbitals have a dumbbell shape. Yet when we put them together, we can see that the lobes on, like a p orbital that has 2 lobes, but they're distorted, whereas a p orbital, both lobes had the same size, same distribution. Now, this right-hand orbital, the one shown in red here, is getting a little more spherical, right? The blue lobe on the orbital is significantly smaller. So it's almost more baseball bat shaped, if you want to think of it that way. But the point is that you are changing the nature of the orbitals where these electrons are going to be residing. So how do we make these bonds? Well, on the carbon, we've got those 4 degenerate sp3 hybrid orbitals arranged in a tetrahedral arrangement. You have hydrogen, which has its singular 1s electron, and so it's got a half-filled orbital. It's going to come in and it's going to share its electron and share carbon's electron in the sp3 hybrid orbital, and it's going to create what we refer to as sigma bonds. And the first connection that's ever made between any 2 bonded atoms will always be a sigma bond. Now here's where we're going to need to go off-road a little bit. So in your notebook, you should have a second page entitled Sigma and Pi bonds. So I'm going to go over to that, and we're going to talk through what needs to be filled in there, and talk about sigma bonds and also pi bonds, what they are, review that from Gen Chem, and then we'll come back into the PowerPoint, look at a few specific examples. All right, so when bonds form between atoms, they are created by the overlap of orbitals of the two bonded atoms. And so that overlap can occur in one of two places. It can occur along the internuclear axis. So again, what we would call the bond axis. And those are known as sigma bonds. Or once a sigma bond is formed, if there are additional overlaps, these occur around the internuclear axis, the bond axis, and these are known as pi bonds. And so you can see here a visualization. A sigma bond would be if you had two p orbitals that end-to-end overlap, and there's quite a bit of overlap there that you can see. A pi bond, okay, so this line right here represents that internuclear axis, or the bond axis. Notice that the overlap isn't occurring along the internuclear axis, it's occurring around, above and below, and as we'll see, it can be in front of or in back of if we're thinking three-dimensionally. And so in general chemistry, we mentioned sigma and pi bonds. We said that single bonds between atoms consist of one sigma bond. You can see that in the illustration here off to the side. If we need a double bond to satisfy the valence requirements of a given atom, then a double bond will consist of first a sigma bond and then one pi bond. And when we draw the two bonds, it doesn't matter which one is the sigma and which one is the pi bond when we draw a Lewis structure. If we need a triple bond to satisfy the valence needs of an element, then that would be consisting of one sigma bond and two pi bonds. Now let's consider the molecule ethene, or more commonly referred to as ethylene. In ethylene, with the formula C2H4, we see that the carbons are going to be bonded to three other atoms, and that's going to require a double bond in order to satisfy the valence needs of the carbon atom. And so when you only need three atoms bonded to a central atom, that means that you only need two of the p orbitals to be hybridized with the s orbital, which leaves you with an unhybridized p orbital. And so what that does is, once again, we are going to mix the s and the p orbitals. We're going to hybridize them. We put three orbitals in, we get three orbitals out. And these orbitals are going to be labeled as sp2 because we used one s and two p orbitals to make them up. So your sp2 hybrid orbitals are going to arrange themselves in such a manner that they are equally spaced, so they take on a trigonal planar type arrangement, and that p orbital that was left unhybridized is going to be perpendicular to the plane of those three sp2 hybrid orbitals. And so if we go back now to our notes, we can see how the side-by-side presence of the carbons in ethylene will show you that overlap of the y orbital, or the p orbitals, excuse me, with that sideways overlap that's around the internuclear axis. So here you can see a space-filling model of the orbitals in ethylene, and so the purple lobes represent the sp2 hybrid orbitals on each carbon. You can see that internuclear distance, that bond axis between them, you have the overlap of two sp2 hybrid orbitals, so that's your sigma bond. In the second diagram, you can see where the blue hydrogen atoms, the s orbital is overlapping with the sp2 hybrid orbital. That creates a sigma bond to each of those hydrogens. And so then this unhybridized p orbital that's on each of the carbons, notice that they are parallel to one another, and so they can overlap above and below that plane around the internuclear axis, but that overlap is what creates the second bond, or the pi bond, that we see in ethylene. So again, the overlap of the sp2 atomic orbitals, hybrid orbitals, on the carbons creates the sigma bond. The p orbitals are going to overlap sideways to form your pi bond. And when they do, notice that that overlap between the side-by-side parallel p orbitals is very, very minuscule. So these bonds are easily broken. They tend to be weaker than sigma bonds. And these electrons are more accessible from the outside by other molecules. So they are typically indicators of reactive locations within a molecule. Now let's consider the molecule ethine, or more commonly referred to as acetylene. We see from its Lewis structure that it has a triple bond. And so in order for carbon to be able to form these triple bonds, okay, we know that there's going to be one sigma bond and two pi bonds. So that tells us a couple things. First of all, in order to form a pi bond, you know you need an unhybridized p orbital. So if there's two pi bonds there, that means 2 out of the 3 p orbitals can't be going into hybridization. And so what we have, and also because carbon is forming a bond to 2 other atoms, we only need 2 hybrids. So we're going to take one s and one of the 3 p orbitals. We're going to hybridize them, 2 in, 2 out, and we get 2 degenerate, same energy, sp, one of each orbitals. That leaves us with the 2 unhybridized p orbitals, which opens up the ability to form pi bonds to go along with the sigma bonds. And so if we look at the space filling model here, we can see that the sp orbitals on each of the carbons are overlapping end to end along the bond axis to form the sigma bond. The 1s orbital of the hydrogen is overlapping with the sp hybrid orbital of carbon to form a sigma bond on either end. And then the unhybridized p orbitals, one going vertically and the other one going in front and behind of the bond axis, those p orbitals are going to overlap sideways to form one pi bond here and then another pi bond in this direction. If we look at the space filling diagram for acetylene or ethine, C2H2, we can see that the 2 sp hybrid orbitals on the carbons are overlapping end to end to create the sigma bond. And so there are also 2 unhybridized p orbitals on axes that are perpendicular to that internuclear axis or that bond axis. And so when we think about the sigma bonds being formed, you have the sigma bond between 2 sp hybrids to connect the carbons, the hydrogen with its s orbital overlapping with the sp hybrid orbital of the carbon, and we see that on either end, but that leaves 2 unhybridized p orbitals on each of those carbons that are parallel to one another. So the vertical orbitals here are going to share sideways above and below the internuclear axis, and these orbitals, all right, that are kind of sticking out towards you and going back behind the model, they are going to overlap sideways and create a second pi bond. So acetylene has 3 carbon-carbon bonds, a sigma bond, and then 2 separate pi bonds. So when we look at a molecule, how do we determine what the hybridization is going to be? And the answer is that you need to evaluate what's going on around the atom. How many electron domains do you have? Sometimes that's as simple as just looking at how many atoms are bonded to it. Sometimes you need to be careful and thinking about, are there lone pairs of electrons maybe that aren't visible? Now, with carbon, we know that carbon is tetravalent. It's going to form 4 bonds preferentially. So if we simply count up how many atoms carbon is bonded to, oftentimes that's enough to give us an idea of the hybridization on each carbon. Now, the caveat is that is assuming that there's no formal charge on the carbons, and that it is forming its typical 4 bonds. So if it forms 4 single bonds, that requires sp3 hybridization because you need them to all be equivalent. If there is a double bond present, that means that carbon is going to form bonds to 3 other atoms, then we see sp2 hybridization. Remember, the sigma bond and the 2 sigma bonds to the other atoms, those are going to be your hybrids. So 3 hybrids, sp2. If the carbon is bonded to only 2 other atoms, meaning you've got a triple bond or maybe 2 double bonds, that's going to be sp hybridization. So as we go from left to right, looking at our example here, we see this first carbon bonded to 4 other atoms, so that would be sp3 hybridized. The next carbon, 4 bonds, so that's also sp3 hybridized. This carbon is bonded to 3 other atoms. We see there's a double bond there, so that points us to sp2 hybridization. The next carbon, same deal. 3 atoms that it's bonded to, plus you see a pi bond, so that's a clue that that's sp2 hybridized. This carbon, once again, bonded to 4 other atoms, so this would be sp3 hybridized. This carbon, next to the last one, is bonded to 2 other atoms, and we see 2 pi bonds, so we know that's sp hybridized. And the final carbon, once again, is bonded to 2 other atoms, and there are 2 pi bonds present, so that means that this carbon is also sp hybridized.